And you don't need to write this down because you've done it already. And what does RREF of A mean? The reduced row echelon form of A. So you can think about this as a function that takes a matrix as an input and returns a different matrix as an output. And you should be able to tell this really is a reduced row echelon form. Then, what I asked you to do is find a basis for the column space of A and a basis for the null space of A. Now, before I forget, would you be sad if my lectures ended up on YouTube and then everybody just looked at the lectures and never came to class? Would you feel lonely?
No.
So how about if I get the lectures on YouTube and you still come to class?
Yeah.
You wouldn't skip class? Okay. I'm glad to hear that. So we will attempt. I think that's going to happen. Which is good. So you can pause. So the advantages are you can pause me, you can rewind me, and I'll be happy to talk about it again. I won't even bother me.
Who's recording the lecture?
I don't know. There might be somebody in this room with a camera right now.
Listen, are we always going to be on the YouTube?
We're going to try.
Wait, starting this
I think it'll be this lecture.
Nice. Do we have the captions as well?
Yeah, no, somewhere, somebody is recording this.
Okay.
I don't know who or how, but somewhere. You should be able to figure it out once it's posted where that student was sitting, right?
Using linear algebra.
I wish, no. There's somebody recording it on their phone as we speak.
Right.
Okay, Jackson figured it out.
Snitches.
No, it'll be a different channel. Okay, oh, and we were supposed to have a test next week, right?
Next week?
What? Yeah, officially?
Delay it.
Yeah, I'm going to delay it.
Yay!
Okay. So anyway, exam 2, I think officially was scheduled for next week, but I'd rather talk some more, so I'm going to push it back. I made your day tonight, haven't I? It's like a big grin.
Is it supposed to be next Monday or Wednesday?
We're supposed to be next Wednesday. It's going to be a week from Wednesday.
Next one's the 10th.
Yes.
Always on Wednesdays, right?
Yes.
Calendar.
17. Yeah. Today's the 1st. Okay. So anyway, back to the interesting things. Do you see that in the reduced row echelon form of A, column 2 is a multiple of column 1? So 2 times column 1 is column 2. And does that work here too? 2 times column 1 is column 2?
Yes.
So if I was building a basis for the column space of A, I know that I'd take column 1 and reject column 2. So if that's a basis for the column of A, it's just a good list of vectors that span. I need 1, 3, 1, 2. Okay, and then this is why reduced row echelon form has a lot of zeros, and those zeros are in very strategic places. Can I build column 3 out of column 1?
No.
Yeah, you can see it just because we got the 1 here and I didn't have any 1s or they were all zeros before that. So that means that this original column 3 is a new vector, And I'm gonna have to put that in my basis for the column space of A. 3, 9, 4, 9. Can I build column 4 out of 1 and 3?
Yes.
Yeah, 5 of these plus -1 of those. So that is not new. And then finally, can the last column here be built out of the 2 that I had there? No. And that 1 is, I can never turn these zeros into a 1, so that's got to be new. So I've got to do. So my basis for the column space of A, and again, I know we went through this last time, is 1, 3, 2, 2. Say that again?
Does that mean that the basis is no?
Okay. So do you notice that each column that went into the basis came from a leading 1 here?
Yes.
And do you remember the phrase we had to describe the number of leading 1s in the reduced row echelon form of matrix?
Yes.
The rank? And did I tell you what the word dimension means?
Yes.
What is, yeah?
Yeah.
Okay, what does dimension mean?
You told us.
Good, I did. So for those of you who don't remember, remind me. Dimension is the number of elements in the basis.
Yes.
Yes.
So what's the dimension of the column space?
3.
It is 3. 3 elements in the basis, so it's dimension 3.
And rank is also 3.
Yeah, and rank is, so what we have for any matrix is the dimension of the column space of A is equal to the rank of A. And so here's a nice math way of essentially saying that each leading 1 in the reduced row echelon form of the matrix gives me a vector in a basis for the column space. Now, it's going to get a basis for the null space. Is, well, the key idea here is the null space of A is the null space of the reduced row echelon form of A. And this is easy, so I'll call this x1, x2, x3, x4, x5.
Very much.
Of course. Maybe different than what I had last time. I'm good with that. Okay, so if I'm making a solution, x1, x2, x3, x4, and x5, is x5 free or forced?
It's supposed to be 0.
Yeah, this equation forces it to be 0. What about x4, free or
Free.
forced?
3.
I'll call it t. x3,
That's first.
it's forced to be t. x2,
Forced. I mean, 3 to be S.
and then this is -2s minus 5t. So what I get is that if this is a vector in the null space, I can write it as a -2s s 0, 0, 0 plus -5t 0 t t 0, which I can write as s times -21 0, 0, 0 plus t times -5 0, 1, 1, 0. So in other words, is every vector in the null space can be written as a combination of these two vectors. What's a basis? A basis is a good set of building blocks to build everything in space. So the basis for the null space is this. And notice that each free choice that we had here, S and T, ended up being one of the scalars that we use for all those linear combinations. So each free choice gave us a parameter, which ultimately gives us a vector in the basis for the null space. Okay, and then notice where the free choices come from. Was x5 free or forced?
Forced.
It was forced because we had x5 equals here. And what was it, the next forced one? Yeah, x3 was forced because we could solve for x3 equals. So whenever we have a leading one, that's going to be a forced choice. And where we don't have a leading one is going to be a free choice. So the number of parameters is going to be the number of columns without a leading one. Got that? So each leading one is going to give me somehow a vector in the basis for the column space. Each non-leading one is going to give me a free choice, which is ultimately going to give me a vector in the null space. So the second thing is, figure this out. If I take the dimension of the column space of A plus the dimension of the null space of A, it's going to be the number of columns. And this, I mentioned it last time. I don't think I wrote it out this nicely. So this is considered the fundamental theorem of linear algebra, part one. Just like fundamental theorem of calculus has two parts, the fundamental theorem of linear algebra has four parts. This is the first. Okay. So we're in 3.4 right now.
So you finished 3.3 last class?
Yeah, and this is kind of me doing it again. So either you can say 3.3 was finished last class and this is a review,
Oh.
or I finished 3.3 right there. This. It's a 3.4. This is a math puzzle. So horses, we'll start with some facts about the world. Horses have 4 legs and 1 head. Humans, 2 legs and 1 head. So far so good, right? Okay, and I went to a horse show this weekend. So there were a bunch of horses and there were a bunch of humans. And what did I count? I saw 74 heads and 196 legs.
Which
Did you
one?
really?
I did. No, I mean, I don't really go to horse show. This is what I saw. Okay, so I just did a head count, 74 heads. I did a leg count, 196 legs.
So which are the human heads and which are the horse heads?
That's what I want you to figure out. So this is something you give to algebra students. Right, so when you're learning algebra, part of what you want them to be able to do is read a question in English and translate it into algebra. So you are going to tell me how many of each. And do you remember when I told you at the beginning of the semester to bring your packet every day? So I'm glad you brought it today. So pull it out. Anybody not bring their packet? So luckily, I made some extras here.
Okay. I really print this equation.
Yeah, that big packet from day one. Yeah, so pass these around. It's like there's some neighbors. And for those of you who brought it, I want you to look for multi-grid graph paper in the packet. So this is what we're using today. Right there. Again, either it's in that packet or there's going to be used for today. That one, and then that one. So does everybody have one of these? So that was partly me stalling for time to let you work on this. Does anybody have an answer? Yes, Jackson.
So that means that there are, I think, in my opinion, that there might be well, a normal horse show would have about 5 horses at least.
Oh, yeah, but this is my mathematical horse show. It could have possibly a different number. So I just need the numbers here to work out. So could it have been 74 humans?
Yeah.
So how many legs would I have with 74 hundreds? If it was 74 humans, how many legs? Yeah, 148 legs. I wouldn't have enough legs. There's got to be some horses. Could it have been 74 horses?
No.
No.
No, it's way too many. That would have way too many. So somewhere between 0 humans and 0 horses.
Is it not like an algebra, is it not just like the number of heads added together equals 74?
Okay.
And then the number of legs together equals 196?
Except we're going to let X and Y be horses and humans.
Oh.
How many? 8 humans?
Oh, no, 8 horses
8 horses?
and 60.
Wow. How did she do that?
We did it in 11.
Yes, you did. Tell us how you did it. So in kindergarten, while they were trying to color in between the lines, you were calculating humans and horses. How did you do it?
I did X horse
Okay, so X is the number of horses.
and Y is
Very good. So yeah, hold on for a minute. Okay, so this is in general an idea, is we've got 2 numbers here. The number of horses, number of humans. And the math trick that you have been doing since kindergarten is you just make variables for each if you don't know what they are. Okay, keep going.
4X plus equal 196.
Okay, so let me stop there. So what is this equation saying? Yeah, so 4x, 4 times the number of horses, plus 2 times the number of humans. So remember, it's 4 legs per horse and 2 legs per human. So this is a leg count on the left, and that has to equal 196 on the right. Very good. Keep going.
And X plus Y equals 64.
Excellent. Well done. So do you see that second equation? It's if you have X horses and you have Y humans, then the number of horses plus the number of humans has to add up to the total number of heads. So far, so good? Okay. And how do you feel about taking this system of equations? There you go. You're getting X equals 8 and Y equals 66. Okay.
I got different names.
Got it. So are there other numbers here?
Oh, by the way, this
Practice can do.
Mr. Smith, there's like an eraser like thing in there that I found.
Where?
In there.
Oh, right on. You rock. Thank you. Is this a good one?
I don't know.
No, actually, I appreciate it, but it's kind of flimsy.
I actually didn't see it.
So I'm gonna pass.
I saw it.
Appreciate it. Okay, so anyway, there's some numbers here, and the new theory is it's something different. 24 horses?
Yeah.
Should be 50? Is that right?
There's also an easier way to solve it.
Yes, there is. Let's hear it.
For every time you substitute in a horse for a human, you gain another 2 legs.
Yes?
And so if there were, if there were just 74 humans, then you would have whatever 74 times 2, 148 legs.
Right.
But you have 196, and that gives you however many 48 extra.
Got it. So yeah, let me catch
divide
up
that
to
by
you.
2, and
Absolutely
you
right.
get 24 more horses.
Okay, so what I like about this problem is you've got different approaches, and they're all interesting. So this is how you tell a kindergartner to solve it, right? So write this equation, write that equation, and then solve the equations to get x and y. Okay, I don't know if you heard about this, if you heard this solution. Is first, let's just imagine that we had a bunch of humans. So in other words, if we had 74 humans and 0 horses, what's the leg count? 148 legs. How many legs do we need? So that is, we need an extra 48 legs. So what we're going to do is if we remove a human and replace him by a horse, what happened to the head count?
Stayed the same.
Head count stayed the same. What happened to the leg count? Yeah, it went up by 2, right? So every substitution of a horse by a human is going to increase the leg count by 2. So we need 48 more legs. So how many horses do we have to add? We have to add 24 horses and take away those 24 humans. And that's 24 and 50. That's another way to do it. And let me show you yet another solution. I'm glad you came up with that. Most people just get the first one. Is I'm going to actually make some new creatures. Is I'm going to call a hypercentaur. 1 horse plus 1 human. And an anti-centaur is 1, or actually I guess I'm right, -1 horses plus 1 human. Let's make some new creatures. What is the count on the hypercentaur? How many legs and how many heads? So a hypercentaur has how many legs?
6.
And how many heads?
2.
And an anti-centaur? No?
0 heads.
Okay, so
0
0 heads, right?
How would it
And
live?
-2 legs.
It's a -2 heads.
How could somebody have -2 legs?
Yeah.
Okay, you great?
You're making a horse.
Can you draw a picture?
No. Not. So it's the only way to get ahead is with a hypercentaur. So in this system, if I'm trying to do it with hypercentaurs and anti-centaurs, the only way I can get heads is with the hypercentaurs. So I had 74 heads, and that is, what, 37 hypercentaurs? Right? And those 37 hypercentaurs are going to give me 222 legs. So if I add some anti-centaurs to the mix, that is going to reduce the leg count. Okay, so how many anti-centaurs do I need? Well, actually, I'm trying to get to. I erased them. How many legs? 196?
196.
basically, I have to remove 26 legs. And the way I remove a leg is that I add an anti-centaur.
And 26 of them.
How about 13? Because every anti-centaur has minus 2
Oh,
legs.
yeah.
So 13 anti-centaurs.
Oh, and then you six it together.
Yeah, exactly. And then a hypercentaur is what? So let's make this horses and humans. So our 37 hypercentaurs is how many horses?
37.
Good. The hypercentaur is 37 horses, and it's 37 humans. And our 13 anti-centaurs is how many horses is an anti-centaur?
Negative 13.
So we have negative 13 horses and 13 humans. So yet again, the 24 and the 50.
How do you get 57 and 15?
Oh, so a hypercentaur is 1 horse plus 1 human. So if I had 37 hypercentaurs, that's 37 horses plus 37 humans.
So you just came up with 37.
Oh, I knew that I needed 74 heads.
Oh,
So in each hypercentaur, the only way I can get heads is with a hypercentaur. So the anti-centaurs are not going to add anything to the head count. So this is how I get all the heads. And then the anti-centaurs will keep the head count the same and drop the leg count.
so how did you determine the number? So you said 37 times 6. Oh, okay. Okay,
You follow this?
yes.
So let me show you the linear algebra way to look at this problem. Is my input space is x is going to be my number of horses, and y is going to be my number of humans. And then, for every horse-human pair that I have, I've got a head and a leg count. So let me just make sure I do this the right way. So what if I pick the point 1, 3 in the input space? Well, what does this code up? How many horses? 1 horse, 3 humans. So how many heads is that going to be?
4.
Going to be 4 heads, and how many legs?
5.
So,
4 and 10.
so it's 4. So that's 6. So there's 1 horse, so 4 legs, and 3 humans. So that's 6 legs. So agree that this horse-human combination gets mapped to this head-leg combination? So if you think about, we've got a transformation that turns horse-human pairs into head-leg pairs. And that transformation is exactly what I erased here. Is if xy is the input, is the head count is exactly like you had, x plus y. And the leg count is 4x plus 2y. So again, the linear algebra way of looking at this is we have a transformation that takes number of horses, number of humans. So that vector represents the start. And then it's as an output vector, we get number of heads and number of legs. And so the problem we had was you want to figure out if it's 74, write this down here. and 196. So here is my target output point, and you're trying to find the input in this space that lands to that one. And where this comes from is the two basic pieces that you have are T of 1, 0, so 1 horse, 0 humans, goes to 1 head and 4 legs. And T of 0, 1 goes to 1 head and 2 legs. So those are the basic, the two basic units we had here are 1, 0 and 0, 1. Okay, what did I do? Is I made a new system. It's what's the vector code for the hypercentaur?
Ooh,
Ooh. What is it?
technically it would be, so it'd be, like, 2 for X, is X heads?
Okay, actually, so be careful. Is the hypercentaur was a vector in the input space? So what was a hypercentaur? Is 1 horse, 1 human. So my hypercentaur is 1, 1. 1 horse, 1 human.
Anti-centaur is gonna be -1, 1.
Yeah, so that was -1 horses and 1 human. So what I did was instead of using my normal coordinate system with 1, 0 and 1, 1, instead is that was my 1, 1. And this is my -1, 1. And so instead of the normal x and y axis, I made this a new axis I'll call x hat. And I'll make that a new axis I call y hat. And then the reason I like this is if I'm trying to figure out where 1, 1 goes. This is one of my basic building blocks. So this is a hypercentaur, 1 horse and 1 human. How many heads? 2, 6. And my other basic unit, my building block in this system, is -1 horses and 1 head. What's this one? 0, -2. So remember, is the linear algebra way of looking at this problem is you want to find the input point that maps over to the 74, 196. And the nice thing is this 1, 1 maps to 2, 6. And this -1, 1 maps to 0, -2. So on the output side, I'm trying to build this vector.